We had actually covered reputation coding. Today we will start studying beyond reputation coding. Uh, Before I go any further into this section, so I would like to go to the appendix. Um, as you could see that one student in the last lecture, he said that is coherent combining, where you multiply the input signal or the input vector with the channel coefficients or with the normalized channel coefficients. So the question was why we are using that type of coherent demodulation. So actually the answer would have come in the future lectures, but I thought that already he has asked a question, so why not give the answer in right at this place. So this will be also useful in the future. Now we have seen that for vectors the error is given as follows. For scalars, this will be simple UA UB, where U and UB are just scalars. All right, and error will be Q times this, Q bracket into this. Alternative view could be that I could write my signal as follows. Here you could see that if x is equal to plus half, then in that case plus half, this will become plus UA, but this will be minus half b, this will be plus half b, this will cancel. So u will be equal to UA if x is equal to plus half. Or if in other words x is equal to minus half, then you can very well see that UA will cancel and minus minus plus half and plus half, this will become UB. So we can just say that the information is in x, and if we are able to detect x, we can just find whether UA was sent or UB was sent. Now actually we know the signal that is being sent is UA or UB plus W. The signal you could see here is actually U plus W, where U could be UA plus UB. But we are trying to develop an alternative view that the signal sent vector can be actually represented by a simple scalar x. Now I can also write my y minus half UA plus UB. So y is equal to U plus W. If I subtract this thing, so W will be just W, but U minus this. All right. So if I do U minus this half, so this half cancel, I will be only the first term will remain. So y minus half will come out to be x times this plus W.
सर ये derived expression है appendix A 3.8 A.38.
Derived expression. Yes, you can see it is a driven. You can also say it is a driven expression. You can just very well see that just by changing the value of x to be half or minus half, you can either get UA or you can get UB. So you have just driven representation of the vectors in terms of the information of a scalar. You
So
just need
इसमें
to know the
channel
value
gain
of x. You just need to know the value of x, and if you know the value of x, you can find whether it was UA or UB that was sent. Haji, what is your question?
सर इसमें हमने लास्ट टाइम पढ़ा था कि जो यू ट्रांसमिटेड सिग्नल है वो चैनल गेन मल्टीप्लाई बाय इनपुट सिग्नल है तो इसमें चैनल गेन वन है यूनिट है
Acha. No, you are right. When we receive the signal, we have HUA minus HUB and all that. But here, what we are developing here, we are just developing the detection rules. And detection rules, we started with just y is equal. Here, you cannot see any h. All right. Here we just have y is equal to u plus w. All right. Just see this from detection. Here we just have y is equal to u plus w. All right. And yes, we mapped this equation. And yes, we mapped this equation to our uh, applications in communications. Okay, but when we are studying from purely detection point of view, we will be just saying that we are just sending UA plus W. Okay. Yes, when you will be applying that, you can say UA is equal to H into UW or UA or H into UB. That is another thing. Here we are just discussing in terms of U plus W is equal to Y. It is from pure theoretical point of view. Application will come in the chapters that we are studying.
सर इसमें एक बात है कि सर ये तो सिर्फ बीपीएसके के लिए होगा सर, जो दूसरी टेक्निक है उनके लिए नहीं होगा।
बीपीएसके के लिए होगा। First of all, this is a vector, so BPSK has to be converted into a vector. All right, so you might have diversity, all right, or you might have some higher modulation scheme. Yes, if it is simple UAUB, you can say it is a simple BPSK, but if it is a UAUB vector, all right, then you have to actually explain. If you want to map it into some application, you might say, all right, it was modulation, BPSK modulation, but I was sending it L times, that is why I got my UA. All right, so there needs to be a link of this vector form to the actual modulation technique. That link we are covering in the relevant chapters. Here we are just developing the theory as well as the answer to your previous question in the last lecture. All right, so you could see that this is equal to this thing. Now here we can very well see that the information is just in X, and that information is just lying in this unit vector. So you could see here that my X is along this thing. All right, so if I normalize UA minus UB divided by its norm, this will be its unit vector. This is a vector here. So I just need to basically focus on this direction, which is UA minus UB. What is UA minus UB? Just like R minus R dash in electromagnetics. All right, position vector of this minus position vector. This is a straight line vector. R minus R dash, a vector going from R dash, the source vector, the source position, to the test point, as you saw in electromagnetics. So this is a simple vector going from B to A, and then normalize. This is a direction going from B to A, but a normalizer, or just a unit vector. This is a direction. So we just need to focus on this direction. All right, and so we will be studying also rest, but you can see that in all of our coherent modulation or coherent demodulation, when we were multiplying by H, we were actually finally converting our expressions to these things, UA minus UB expressions. Finally, they were coming out to be UA minus UB expressions. So they can only be achieved once we multiplied our input signal with these types of vectors. They are here, they are these V's vectors in this direction, but in implementation, it comes out to be an H vector. Let us try to go further. Now, so Y is a vector, the received signal. Now it has different directions. Some directions are orthogonal to V, and those directions that are orthogonal to V, they contain only pure noise. And we know noise is, all that Gaussian, circular, symmetric. If it is real, it is real, but still, it is wide Gaussian, Gaussian random variable. If it is complex, then it is circular, symmetric, and all that. While noise in these directions is also independent, so noise in the other directions, other than this direction, is not only independent to this direction, but it is also independent to the noise in this direction, or the noise in the signal direction. So you can say that the components that receive vector in these directions are irrelevant for direction. So we do not need to go into other directions. We just need to concentrate on this direction. That is why we mapped our signals to these directions. Similarly, in in the lectures, in the chapters, we were mapping it to h of t. Now let us try to understand it further. So what we will do, so this is the received signal. All right. I have deliberately subtracted the mean of the mean vector from the receive vector, and I will map this, okay, to my signal direction. All right, and this will be the this will give us the necessary information for detection. If you have mapped the receive signal to this VT direction, which is just the the vector between U and UB, okay, you will get the right statistics for doing the proper detection. And hence, because of this dot product, you would have converted the vector detection problem to a scalar detection problem. So you can see also in this figure here. So this is a vector UA minus UB, and this is the receive vector. So you take the dot product of y, or you take the projection of y on, this is the v vector also, normalized version, this is the v vector. You just take the projection of this vector here, and on this projection you will make a decision whether the sent the sent actually x is equal to half or minus half. In other words, you can say whether the sent vector was UA or UB. You can also write it like this also, that we are viewing the receive vector in a different orthonormal basis. The first orthonormal base is the v vector, and other directions, as I've said, are orthogonal to v, as well as among themselves they are also orthogonal. So we have an orthogonal matrix whose first row is v, and the other rows are orthogonal to each other and to the first one, and all of them have a unit norm. So if I orthogonalize, or if I multiply my received signal, y is the receiving, but I've taken out the mean, with this orthonormal matrix. All right, so yes, there will be vectors. I will also try to do this some of in my notes. All right, this is your orthogonal vector. So I will put this orthogonal vector, I will multiply with this thing. All right, we know that y minus half is actually equal to x plus w. So I will be multiplying this O orthogonal matrix with x as well as O with w. Now when I will multiply my O with x, so I can very well see that all of these O's rows, they will be 0 with x, because they are all orthogonal to this direction, and I know this direction is the v direction, but only the v direction that will go along with this direction. This will only multiply with this, while all other will go 0. Okay. Similarly, O with W. So this is the orthogonal transformation with W. So I will be just interested in the first row, because next other will be 0. So I will just get the first element of my vector, which will be equal to this thing. This is the v vector times this thing, and I will also be interested only the first the transformation, and the first transformation will be again Gaussian noise. Its status will not be changed by multiplying it with the orthogonal vector. So UA minus UB, this will become UA mod square, 1 cancels, so you will get x into UA minus UB plus n0 n0 by 2. So this is the received statistics. So received statistics comes out to be just x times the difference between the mod of the two vectors, which is a scalar quantity now, plus the noise. So our projection gives us just this thing, and you can compare this with the previous. So for 2 dimensions, this will be plus half, it will be minus half. For symbols, plus and minus half, this distance will be plus half. For minus and minus half, the distance between them half half, half minus minus half, this will be plus half, this will become half plus half, this will become the distance. So this is a scalar distance now. Just put this scalar distance in the formula of the scalar. and you will get the same result. The only change was that previously you had UA, UV, which were already scalars, and you just have one, one one line, which was just representing the magnitude of the scalar. Now you have UA vector, UV vector, and you are representing this with a mod of a vector. This is the only change. And sorry. So we call this the sufficient statistics Y. All right. Which comes after a projection of Y, onto the V vector and all that orthogonal matrix. You can also say a sufficient static in the projection of V, and that is why it is called a match filter. This operation is called a match filter because you project of the your received signal in the direction of V. Okay, and it is achieved by a projection of the received symbol with H.
सर V और U एक ही चीज़ है, ट्रांसमिटेड सिग्नल।
V और U, no, V and U are not. No, V and U are not the same thing. All right. V is the direction on which you have to project your received vector. All right. So it is a vector. It is a unit vector. All right. While symbol is a symbol that you have actually sent. All right.
सर V itself क्या मतलब कि हम ट्रांसमिट कर रहे हैं U और रिसीव कर रहे हैं Y और चैनल है H, तो V क्या रिप्रेजेंट कर रहा है मॉडल में?
V is the unit vector on which you have to project your Y. So it is a straight line, as I've told you, R minus R dash, straight line connecting UA with UB. An exact vector representation will be a vector starting from B and ending up to A. So you have to project your received vectors onto these V vectors to get the scalar projection on which you can make your decisions or your detection decisions.
Okay, sir.
All right, so you can see that yes, error probability depends on UA/UB or the distance between them. Yes, noise is always isotropically, so it is rotationally invariant. So it only depends on the distance. That's a very important thing. And we saw that final detection comes out to be x times UA minus UB mod, plus W. So you, as I just showed in my notes, it comes out to be this error. And you can actually generalize this to, for example, if you say, no, I don't have only two vectors, I have m vectors. U1 going from UM. In that case, you will project Y onto the subspace spanned by U1 UM. Here you are projecting it into UA minus UB because UA minus UB defines the space R minus R dash or the region. अब देखिए ना जब R minus R dash करेंगे you will get a 2-dimensional or 3-dimensional space which basically, or plane, which actually covers all the transformations of R minus R dash. So if you have many vectors, you will form their subspace and you will project Y onto that subspace. Once the projection is done, you will get a scalar number. That will be the sufficient statistics. In case of PAM, where all these UMs, they are actually same direction because PAM, all the symbols are in a straight line. So these are in a single direction of H. So then no problem. This H is this H is sufficient because you have only one vector. In this same vector, all the other vectors lie. So this is sufficient for projecting. All right, you can just project Y directly onto H. So projection onto the direction of H directly you can project because all the vectors they lie on this H.
Sir, PAM modulation technique.
Yes, ma'am. Is we studied this in the last lecture. For example, we I told you minus 3b minus b plus b plus 3b. All right, all the symbols were on a straight line. We compared this, with the BPSK, or with especially with the QPSK, where the symbols were in two-dimensional line in the I and Q channel. This only has symbols in the I channel. Okay, and they are more than BPSK, or they could be 4 PAM, 8 PAM, and so on and so forth.
Okay.
Now, as you know, one student just asked a question that in the in the book, the symbol that we receive is definitely H into U, H into UA, UB, or whatever the vector. Yes, you are right. The received signal has to pass through a channel and it will become complex. Okay. So what to do for complex? All right. So I think we should finish this right here, or at this moment also. So now again we have U, and but we have UA, UB, and these U and UB, they could be now complex. So receive vector will be now U plus W, where U could be a complex. So each is a complex and a variable. So total it will be a complex random vector. And similarly, W will be a complex. Each will be a CN, circular symmetric complex Gaussian and a variable. But the vector will now become a vector. CN, you know this now. N not I. We studied in the last lectures why this becomes N not I. It's covariance. Now, so how to find? Again, same principle we will use. We will try to project our received complex signal into the subspace spanned by my vectors UA and UB. All right. Here it is UA and UB, but in industry, or in applications, it will be whatever the received signals they can take the form. You will be projecting onto those. So let us try to understand here for theoretical point. So again, I can write my vector as follows. No problem. Yes, alright, UAB, they are complex, but still I can just write it in terms of my x. Alright, x, as we did in the previous case. Again, you can see that the signal is in this direction, because x information lies in this direction, and it is sufficient, because if I know if x is half, I will get UA. If x is minus half, I will get UB. This x information is sufficient, and this x lies in UA minus UB. So what I will do, the same thing. I will subtract the mean, project this onto the receive signal direction, which now I will take complex conjugate. Previously it was transposed. Now because it is complex, I have to take complex conjugate, and I do this multiplication. And when I will do this, and we saw earlier also, first of all, y minus half, you will get x UA minus UB, plus W vector, all vector. When you will multiply with B conjugate, this will become x UA minus UB plus W. Same thing will happen as we saw previously. All right, only it is now a complex. And why this? Previously it was coming out to be n naught by 2, now it will come out to n naught, because it is now totally working in the complex domains, real and complex domain at the same time. Again, you can form the real part, you can get the same real part with the same real error, with the same error probability as we saw previously. Similarly, you can take the imaginary part, you will get the same error. And If you combine them, again you miss some steps, but you can see here. Yes, if I just take the real, I will get the same error of the real vectors. If I get the imaginary, I will get the same vector. And if I combine the complete, so I have half of probability of error in both the independent. So the overall error again comes out to be the same thing. The only change is now UA is a vector, but is now a complex vector. UB is a vector, now it is a complex vector. So the formula remains the same for all the cases. Okay? But just your UA will change the form from real complex vectors, real vectors to real numbers or complex numbers. So again he is saying the same thing. We have more than two possible transform vectors and they are of the form H into this thing. Alright. Where X is complex value. Alright. Then all of them are now having this H vector. Their space is now being defined by H. So you just have to project your receive symbol onto this H, and that is what we were doing. Now coming back, so now we will try to understand beyond repetition coding. Now what is the dilemma? We could see here that if I apply repetition coding, yes, I get a diversity gain because I repeat my symbol, but you could see I am not exploiting my degrees of freedom because I am taking two symbol times, or let us say if I am repeating L times, I am taking a space of L for just sending one symbol. I am taking L symbols time. So I am not utilizing my degrees of freedom are L, but I am just sending one data. But I am getting again L gain, diversity gain. So we will go to sophisticated codes where we have the diversity gain as well as जी
सर ये है कि हम देख रहे हैं कि वो सर लास्ट वाले में से वो सवाल ये है कि हम देखते हैं कि 4 एक दफ़ा सेंड हो रहे थे सर 4 कोड्स एक वक्त में, तो सर उनको पीछे स्टोर भी तो कहीं करना पड़ता होगा ना, और सर उसको देखना पड़ता होगा जो स्टोर कर रहा है कि मैं उसको डिलीट करूँ ना करूँ, तो सर वो कौन हैंडल करता है?
अच्छा 4 पेजेस जा रहे हैं, 4 मतलब आप क्या मतलब जो अभी हम पढ़े थे
सर 4 कॉर्पोरेट्स कह रहे हैं
ये जो अभी हम पढ़े डिडक्शन के लिहाज से, थ्योरेटिकल डिस्कशन के लिहाज से कह रहे हैं
सर ये लास्ट लेक्चर में से है सर, इस लेक्चर में
लास्ट लेक्चर में हो यार ब्रदर पिछले। अच्छा क्या लास्ट लेक्चर में कहाँ से बताएं फिर
सर ऊपर सर और
सर ब्लॉक डायग्राम से ब्लॉक से 4 ब्लॉक्स एंड
अभी
ये
इनको बोलने देना, इनको तो कहना। हाँ जी आप बताएं ना, जो
सर ये
आपका नाम साद है ना?
जी सर।
हाँ इधर से आप कह रहे हैं?
तो सर ये देखें,
हाँ
जी सर, इसमें देखें सर, हमें अगर एक ही कोड को 4 दफ़ा सेंड करना है 4 डिफरेंट टाइम स्लॉट्स में, तो सर हमें उसको सेव भी तो करके रखना पड़ेगा ना कहीं पे कोड को, तो सर फिर हमें उसे डिस्कार्ड भी करना है क्योंकि हमारे पास बफर इनफिनाइट मेमोरी का नहीं होता, तो सर ये इंफॉर्मेशन कौन हैंडल करता है?
ये आप किसी और तरफ जा रहे हैं ना, मतलब पूरा एक कम्युनिकेशन सिस्टम है कि इसको कैसे हैंडल किया जाए। हमने तो बस देखना है कि कैसे गेन मिल रहा है। आपने 4 दफ़ा रिपीट किया ताकि आपको कहीं ना कहीं अगर फेडिंग भी आती है तो आप उसको रिकवर कर लेंगे। तो जाहिर है जब उन चारों को यूटिलाइज करके आपके पास एक सिंबल आ जाएगा तो बस ठीक है, फिर आपको तो 4 की ज़रूरत नहीं, जो एक सिंबल है उस पर आपने डिटेक्शन किया है और वो डेटा फिर आगे जाएगा डिटेक्ट करने के बाद। तो अब ये बफर है, ये
सर
सब तो मतलब सिस्टम अपना डेवलप करना पड़ता है आपको। जाहिर है 4 को लेंगे तो फिर एक निकलेगा, मगर फिर उसके बाद 4 की ज़रूरत नहीं है, 4 को आपने ख़त्म कर दिया।
ठीक है सर,
एक से
ठीक।
उनको 4 को ये डिटेक्शन वगैरह करने के बाद आपके पास एक डेटा आएगा कि जी मैंने ये सेंड किया था, बस एक सिंबल आ जाएगा, फिर उस सिंबल को आप आगे रिसीवर को
यस
भेजेंगे।
सर, लास्ट में हमने ये भी देखा था कि ये जो फेडिंग है या ये जो, तो ये 100 टू 100 100 तक जाती है, 100 डेटा लेवल्स की या 100। तो सर इसमें तो ये 16 शो की हुई हैं, तो सर ये तो अगर फेडिंग ऐसी आ जाती है जो इन 16 के 16 को खा जाती है, तो सर फिर तो हमें ये फायदेमंद नहीं होगा ना सर।
16 के 16 को नहीं खाएगी ना, ये आप समझ इंटरलीविंग आपको करना पड़ेगा ना। हम जो अगला सिंबल भेजेंगे वो नेक्स्ट कोहेरेंस टाइम में भेजेंगे। कोहेरेंस टाइम का मतलब होता है कि वो जो चैनल होगा
सही।
अगले टाइम में वो अभी से बिल्कुल डिफरेंट होगा। तो अगर 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 आपको अगर आपने 10 दफ़ा रिपीट किया तो 10 डिफरेंट कोहेरेंस टाइम में आपने इसको भेजा होगा, तो कितनों में फेडिंग
ठीक है सर,
आएगी।
ठीक है,
अच्छा,
ठीक है सर।
अच्छा। So now we try to study sophisticated codes so we could get diversity gain as well as we could get better degrees of freedom. So we will see that by using codes you will be getting another gain that is called the coding gain, which is beyond the diversity gain. There are many types of codes, but we will be first of all considering on rotational codes that we could understand some of the issues of designing codes for the fading channels. So we take the case for L is equal to 2. This means we are using 2 coherence time. We are just repeating the signal once. Alright. Once it will be sent and will be again repeated in some other coherence time. This is meaning of L is equal to 2. So we have a BPSK symbol and the BPSK symbol could be +1 or -1. If I use L is equal to 2 and let us say I use rotational codes, repetition code. First of all, let us say I use repetition code. So I will send A, then I will send again A in another coherence time. And that case, we have seen previously, you will get a diversity gain of 1 over SNR square, but not more than that. But but drawback will that you will be taking 2 symbol times to send 1 bit or 1 symbol. If for example I send 2 different symbols in 2 slots, then very good, I will be getting available degrees of freedom, more efficient, I will have greater rate. But problem is that I will not then get diversity gain. I will have no repetitions, no diversity gain. If it is in a fade, I will lose everything. Alright, so in that case I will get no diversity gain. In the first case I will get not able to efficiently utilize my degrees of freedom. So I have a dilemma. Okay, I take one decision, I get one benefit, but I lose another benefit. So what is the intermediary solution? Solution is that in order to get both the benefits, okay, we use a scheme that transmits the vector in this form. So what we do, we send two symbols, two different symbols, all right, u1 u2, all right, but they are now sent in form of a vector, all right. This vector is multiplied with this rotational matrix, all right, where theta is some value, and in that way I will get 4 different code words. You will say, how sir? Now this is a 2 cross 2 matrix. 2 cross 1 multiplication will give you 2 cross 1, so we'll get a 2 cross 1 vector. And what will be the values of u1 u2? They could be any BPSK values. They could be AA, minus A minus A minus A, or minus AA. These could be the values. Each of these vectors, if they are multiplied with R, I will get vector XA, XB, XA. And remember, XA is a full-fledged vector. It is a 2 cross 1 vector. This is also a 2 cross. These are all vectors. Okay. They are shown in figure 3.8a. So this is on my original AAA minus these are my BPSK symbols in terms of a vector. Remember here that there are 2 dimensions. So for x1 could be plus a minus a. Similarly, x2 could be plus a minus a. But these 2 dimensions are at different times. So if you multiply this with rotational, you will get a transform value of XA, XB. Okay. So, it will be something cos and sine multiply and some, you will be seeing its mathematics in detail. So now you have these types of vectors which are actually like AAA, but they are, rotationally, they are rotated with respect to the original directions. And they are shown here after rotation. These are the new positions. As you can see, this box has been rotated from the original box position in this direction. Now the receive signal, so I will be receiving X of A, but we know that this X of A will pass through a channel. So X of A1 plus into H plus W, X of A2 into H plus W. So your Y file will be your whatever the X here into the appropriate H plus W. Remember here that this X is getting 2, but these 2 are being sent in different coherence times. That is why their channel coefficients are different. All right, L1 is L is equal to 1 and 2. So when it is difficult to obtain the error probability functions, we use the famous union bond. And what is a union bond? Union bond says that if you want to find the error probability for multiple signals, as you know, here we have XA, XB, XZ, XD. Okay. You just assume that only 2 symbols or 2 vectors could be sent. Just find the probability of error from these 2. Alright. Now we actually know that XA was sent. So error could be that either XA confuses with XB, XA confuses it with XC, or XA confuses itself with XT. The union bond says that the total will be less than the sum individual probabilities of confusion between the two vectors XA and XB. Alright. So XA cross arrow XB means it is the error probability of confusing XA with XB when XA was transmitted.
सर ये स्टेटमेंट समझ नहीं आई जो आपने बताई, इसको काइंडली जरा
सही। लेकिन अब probability of error अगर आपने निकालना होता है इसका एक प्रोसीजर होता है। आपने जैसे कोई सिंबल यहाँ पे लिया, बस ये रिसीव सिग्नल था। अब आपने देखना है कि वो जो सिंबल होगा वो किसके रीजन में जाएगा। अब 4 आपके पास वेक्टर्स हैं, तो वो तो चारों के साथ फैसला होगा।
yes.
तो ठीक है ना, तो एक साथ इसमें ना डिसीजन रीजन्स बनाए जाते हैं। डिसीजन रीजन्स अगर इतने इस इलाके में आया तो इसका इलाका है, अगर इधर आया तो ये बी का इलाका, इस तरह से बनाया जाता है। पर वो जो डिसीजन रीजन्स हैं वो भी आपको इनको आपस में कंपेयर करना पड़ता है, इनकी प्रोबेबिलिटीज को। ठीक है, और फिर जाके आप एक इलाका बनाते हैं कि भाई चलो ये इसका इलाका है, उसका इलाका, इस तरह से। बहुत दफ़ा आप सिर्फ 2 को कर लें फिर बन जाता है, मतलब बहुत दफ़ा आपको चारों को, जनरल रूल में तो चारों को देखना पड़ता है अगर आपने कोई बॉर्डर बनाना है। यानी अब एक्स बी का फर्स्ट करेगा ये बॉर्डर बनेगा, इसका मतलब है आपने एक्स बी की प्रॉबिलिटी को कंपेयर किया सबकी प्रॉबिलिटी के साथ, और क्योंकि एक्स बी की प्रॉबिलिटी ज़्यादा थी इसलिए ये सारा इलाका जो है वो एक्स बी का हो गया। ठीक है, मगर ये एक डिफ़िकल्ट चीज़ है। तो यूनियन बॉन्ड वो कहता है कि जब आपको जैसे मल्टीपल वेक्टर या मल्टीपल आ जाए, आपको फैसला करना पड़े, तो आप ऐसा करें, आप अज्यूम करें सिर्फ 2 ही रखे हुए जी, सिर्फ एक्स ए और एक्स बी है बस, उसका प्रॉबिलिटी फेयर निकाल लें। फिर आप कहें जी सब गायब हो गए, सिर्फ ए और सी है। अब हमें तो पता है कि हमने एक्स ए भेजा था, तो एरर क्या हो सकता है? एक्स ए को आप कंफ्यूज करेंगे बी के साथ, ए को सी के साथ, या ए को डी के साथ। इन तीनों को आप यूनियन बॉन्ड करते हैं, इन तीनों को अलग-अलग तस्वुर करें, उनकी अलग-अलग प्रॉपर्टीज निकालें, आप फिर सबको ऐड कर दें, तो ओवरऑल एरर हमेशा इससे बाउंडेड होगा। दिस इज यूनियन बॉन्ड। Union bond details are also given in our course book of the undergrad, but it was not actually covered in detail in the previous years. But from this year, as we are actually covering PAM, multi-signal PAM, like this 4 PAM or 8 PAM or 16 PAM, that is why now undergrad students will also be aware of this union bond.
सर मींस हर एक की प्रोबेबिलिटी इंडिपेंडेंट है फिर?
हाँ, ये यूनियन बॉन्ड एक बकायदा इसका है, इसका कॉन्सेप्ट है। वही कहता है कि बजाय कि आपको तो सारों को देखना है एक साथ, आप मत देखें ना, आप तो सिर्फ 2 ही भेजेंगे, एक्स ए और एक्स बी, ठीक है। फिर आप कहें सिर्फ एक्स ए एक्स सी में ही झगड़ा, वरना एक्चुअली तो एक साथ 4 चीज़ों का झगड़ा, मगर आपने उसको मतलब उसको थोड़ा सा आपने एक बॉन्ड निकालना, आपने एग्जैक्ट एरर की नहीं, आप एक बॉन्ड निकाल रहे हैं। ये चलो मैक्सिमम तो इससे कम ही होगा ना, हाँ मैक्सिमम लास्ट बार इससे कम होगा, क्योंकि अब आपने जब इसको कंसिडर किया तो ये सारा एरर आ गया इन दोनों का खाली, जब आप तीनों का सारा से ऐड करिए तो कहीं गुना उससे ज़्यादा हो जाएगा जो चारों कंबाइन करने से मिलना था।
सर मींस के हमने हर कोड वर्ड के अगेंस्ट 3 कोड वर्ड्स की प्रोबेबिलिटी देखनी है, यानी एक्स बी के लिए भी सेम प्रोसीजर होगा, एक्स सी और एक्स डी के लिए भी
हाँ
इसी तरह सर? ठीक ठीक
हाँ,
ठीक है
मगर चूंकि वो तो फिर सिमेट्रिक है ना, आप एक के लिए कर लेंगे सबके लिए काफ़ी हो जाएगा।
ठीक है सर, मैं अंडरस्टैंड।
अच्छा, so where this is a probability of confusing XA with XB when XA is transmitted. When these, देखें क्या लिखा है, when these are the only 2 hypotheses, यानी यही तो इसका फायदा है। आपने बस कहना कि 2 ही भेजे गए तो 2 का निकाल दें बस, फिर अगले 2 का खाली। अब 2 का करना तो आसान होता है, अभी हमने देख लिया कि 2 का करना कितना आसान है। क्या होता है जी, जब 2 भेजे जाएंगे तो क्या फैसला होता है, यू ए माइनस यू बी, खत्म। चाहे वो वेक्टर हो, चाहे कॉम्प्लेक्स वेक्टर हो, चाहे स्केलर हो, फासला जब 2 भेजे जाएंगे तो उनका जो डिसीजन फैसला है वो बस है यू ए माइनस यू बी, खत्म। यहाँ भी यही कर लें आप, ठीक। कंडीशन ऑफ द चैनल गेन्स दिस इज द बाइनरी डिटेक्शन प्रॉब्लम एज आई जस्ट टोल्ड यू इन अपेंडिक्स, ठीक है। ये हमने आसानी कर ली। नाउ व्हाट विल बी, अब वो जो आप मुझे कह रहे हैं यस यूए विल नॉट बी ओनली XA1 and XA2, yes it will be H1 also, all right, because the symbol has to pass through a channel, and UB, the signal part, will also be it will also have passed through some channel.
बट सर प्रीवियसली तो हम इसको इंक्लूड ही नहीं कर रहे थे जब 1/2 यू ए प्लस यू बी कर रहे थे।
जी, मैंने आपको यही बताया था, थोड़ा सा ना आप चीज़ों को इनके कॉन्टेक्स्ट में रखें। वहाँ पे मैंने कहा था कि हम बस देख रहे हैं कि यूए का हमें पता, हमें कुछ नहीं पता कि यूए को आपने अप्लाई कैसे किया इंडस्ट्रियली। हमारे पास सिर्फ मैथमेटिकल डेवलप है कि यूए और यूबी आया है, हमें नहीं पता यूए कितने एच के बराबर है, क्या हमें नहीं पता। हमें पता बस यूए यूबी आया, उनका आपने फैसला कैसे करना है, भाई यूए माइनस यूबी, बस ये है फाइनल डिसीजन।
ठीक है
अब हम यहाँ पे कह रहे हैं यूए क्या होगा, यूए तो यहाँ से आएगा, यूए खाली XA1 तो नहीं हो सकता ना, क्योंकि XA1 को चैनल से पास तो होना है फ्लैट फीडिंग के साथ, और 2 डिफरेंट कोहेरेंस टाइम में जाएंगे तो ज़ाहिर है 2 डिफरेंट आएंगे। अच्छा, अगर हम कंफ्यूज करते हैं यूबी के साथ, तो ये भी हो सकता है कि हम ये कह रहे हैं कि नहीं भाई, आपने तो एक्स ए भेजा ही नहीं था, आपने तो एक्स बी भेजा था उसी टाइम स्लॉट्स में। तो ठीक है भाई, हो सकता है, यही तो एरर है। अब देखना है इनका भाई, इसमें से कितनी एरर प्रॉपर्टी निकलती है, हमें क्या कंफ्यूजन होती है कि हमने यूए भेजा था उसी टाइम पे, हमने यूबी भेजा था। सॉरी, आई एम स्पीकिंग इन उर्दू, आई शुड गो with English. So probability of error now use, you know, simple schemes that we have studied, that क्या कहते हैं इसको, probability of error between two vectors is just ua minus ub. Now again the steps are missing. सही है, so I have just tried to cover it in these notes. Let's see, कहीं ना कहीं तो ये हो ही जाएगा, बहुत से नोट्स में होगा। इसके अलावा इसमें भी मैंने काफ़ी हद तक किया था। चलें अभी इसको इसी में डाल लें। So you want to find ua minus ub mod. Now we know this is ua, we know this is ub. So ua minus ub mod is equal to this plus this square under root. जैसा कहते हैं ना एक्स स्क्वायर प्लस वाई स्क्वायर अंडर रूट, तो वही हो गया। ये इसका ये एक कॉम्पोनेंट है, दूसरा कॉम्पोनेंट इनका स्क्वायर अंडर रूट कर दिया, ये आ गया यूए माइनस यू बी मॉड। फिर ए माइनस बी होल स्क्वायर खोला, ए माइनस बी स्क्वायर, वो ये बन गया आपके पास। फिर एच माइनस स्क्वायर का कॉमन निकाला, तो ये बन गया आपके पास। फिर आपने इस पूरे का स्क्वायर लिया, तो ये सारा बन गया। एच टू का कॉमन निकाला, तो ये आ गया आपके पास। नाउ व्हाट इज दिस थिंग?
सर ए माइनस बी होल का स्क्वायर।
हाँ, ये आपने खोल दिया, एच को कॉमन निकाल दिया, इधर आपने ए माइनस बी का स्क्वायर लिखा, यहाँ पे इसका ए टू का बी स्क्वायर लिख दिया। अब यहाँ पे मैं एक चीज़ डिफाइन करता हूँ, डी वन। डी में मैंने कहा है एक्स ए वन माइनस एक्स बी ओवर ए। इसका मतलब ये हो जाएगा डी वन स्क्वायर इंटू ए स्क्वायर हो जाएगा। ये हो जाएगा ए भी डिफाइंड होगा, यानी कि एक्स ए टू माइनस एक्स बी टू over a2 over a is equal to d2. So d2 will be equal to xa2 minus x2 over a square, and then this will come out to be this value also here. देखते हैं बुक कहाँ तक आया था। सो कैन सी ये इसने ये एस एन आर भी किया, वो भी हम कर देते हैं, कोई बात नहीं। अभी हमने यहाँ तक किया, so we are here. Next step, you can see I can take a square common. Underneath, I had 2 and not by 2, so 2 comes inside, this becomes 4. 2 4 cancels, we have 2 and not. But this n naught will go with a square. For BPSK, a square n naught is equal to SNR, so I can put SNR. So now probability of confusing XA and XB is equal to this thing. So there is no e minus x2 over 2. So this is my now probability of error. Now again we know, you can go from the book here, that this probability of error, where you could see that we have defined D as follows: xa minus xb over a. It comes out to be 2 cos and 2 sin. Now you will say how this comes, ये मैंने फिर अगले लेक्चर में यहाँ पे इसको Alright, D is equal to this thing, so this you can basically, oh yeah, yes. So you can get your XA like this. All right. Similarly, you can get your XB. You know, XA is equal to RAA and XB is equal to basically R into minus AA. All right. So here you can see only the signs of these factors will change. Oh, sorry, these factors will change because you know A changes to minus A for XB. So these will from plus plus they will convert to minus minus. So this will be XA, this will be XB. So ये थोड़ा सा इधर आ गया मगर you can see XA minus XA 1 minus XB. I take the first two, and you can see I get D cos theta. Similarly, I take the second one. Second of this thing, I will get 2 sine. Alright. That is why I will get 2 cos and 2 sine. Is the normalized difference between the code words normalized such that the transmit energy is 1 per symbol time? Now you can very well see that transmit energy will be 1 per symbol time, because you know if you find the energy of this it will be what? It will be 4 into cos square plus 4 into sine square. 4 commons will become cos square plus sine square. So this will be 2 cos square plus 2 sine square, then you know under root. So 2 square plus cos plus sine square will be 1, and you know 2 square will under root is the cancel, will come out to be 2. Energy is 2, but this energy is 2 for 2 slots, you know 2 time slots of H1 and H2, and you know this means for one symbol time the energy is 1. So this energy D has been normalized so that its energy is 1.
सर
हाँ जी बोले.
सर ये जितने हम स्क्वायर ये जितने हम वेक्टर्स पढ़ रहे हैं ट्रिग्नोमेट्रिक आइडेंटिटीज के मतलब ये किन बेस पे बताए जा रहे हैं? कभी हम स्क्वायर मैट्रिक्स पढ़ रहे हैं, कभी वेक्टर मींस के बैकएंड पे इनके कोई थ्योरी या न्यूमेरिकल प्रूफ्स हैं? जैसे अब हमने डी को इक्वल कर दिया 2 को साइन थीटा और 2 साइन थीटा के, मतलब हम 2
नहीं
साइन
हमने इक्वल नहीं किया, हमने इक्वल नहीं किया भाई. मैं आपको ये बताया ना, आप कैलकुलेट करें ना इस तरह से. आपने x से x भी निकाल लिया.
जी सर.
देखें ऐसे ऐसे कैलकुलेट, यहाँ इक्वल नहीं है, ये निकाल. आपने पहले x से निकाले, ये हमने डिजाइन किया ना एक रोटेशनल मैट्रिक्स, और ये हमारा पुराना वेक्टर, ये रोटेशनल कोडिंग है ना. आपने x से बनाया, फिर आपने x भी बनाया, ठीक है. फिर आपने x से x भी का डिफरेंस लिया, उसके जो टॉप का डिफरेंस लेंगे तो ये आएगा, उसके दूसरे का डिफरेंस लेंगे तो ये आएगा आपके पास, ठीक है. फिर जो डी वेक्टर्स में 2 cos 2 sin थीटा रखेंगे, उसकी एनर्जी निकालेंगे तो 1 आएगा. ये मैं बता रहा हूँ, डी जो एक्चुअली है वो इनका मतलब इनका डिफरेंस है. एक्स का आपको पता ना, आपको यू ए माइनस यू बी करना है ना. सो देखिए ना, ये एक तरह से उनके आपस का फासला दे रहा है आपको, एक्स से एक्स बी का फासला. ऑलराइट, ये उनका डिफरेंस ले रहे हैं. अच्छा, so now you can see that you know error is this, but we can use the bond that q of x is always bounded by e minus x square over 2. So square of this, you know, under root will go away, divided by 2, this will become 4. So I will get this expression. So this is exponential, and then the channels, you know, are mod square. So now I assume that you know h and h1 and h2, we know that h1 and h2 are you know Rayleigh distribution. Our h were Rayleigh, if you remember, h were here Rayleigh. So I find its expectation. ये तो किसी एक h1 के लिए आए थे ना, but I will try to find the expected value of the error. So you know you have to apply the expectation operator. So we apply the expectation operator. Expectation operator. All right. So there is a moment generating function for this. Expectation of the exponential. Of our exponential random variable x is given as 1 over 1 minus s. So I will take its mean because they are h1 and h2 independent, so I can separate them. Mean of this times mean of this, and mean of this I can just apply this operator 1 minus s. So here you know h1 is your h1 mod square is your exponential. Rest of it is just s. So just become 1 minus s, which is just you know minus minus plus snr d1 square over 4. So you will get these two terms. Here you could see that if let us say d1 is 0, then your error will be just 1 snr. So here if d1 is 0, you can see d1 is 0, you will get only 1 snr. If d2 is 0, so you know this will go 0, still you will get 1 snr. So your if you don't have these differences, then your diversity gain will reduce to 1. But if you have these distances, that and you can see xa and xb, they are at distances. All right. But it might happen that because of h, the distances are vanished. But let us assume that if they are those distances, here you know this d, it is just xa minus xb, and there we had put these distances. All right. So if these are distances are not 0, then both will be there. And in case of high SNR, you know one can be neglected. This will become Sn square, d1 square, d2 square over 16. 16 goes in the numerator. So probability of confusion will come out to be 16 over the square 1 over SNR square or SNMR minus 2. So we call this thing as the square product distance between XA and XB. हाँ जी, कुछ पूछना चाह रहे हैं पूछें?
जी सर 16 किस तरह है?
आओ देखिए बड़ा सिंपल है. वैसे तो मैंने शायद नोट्स में भी किया, मगर आप देखिए इन दोनों को मल्टीप्लाई 1 1 को निगलेक्ट कर दें, इन दोनों को सिंपल मल्टीप्लाई करें तो क्या होगा, SNR स्क्वायर हो जाएगा, d1 स्क्वायर d2 स्क्वायर हो जाएगा और 4 4 का 1 ओवर 16. 16 फिर ऊपर जाएगा तो ऊपर चला जाएगा, 16 यहाँ आ जाएगा. इट विल गो फ्रॉम डिनोमिनेटर टू न्यूमरेटर. SNR स्क्वायर हो जाएगा, यू कैन राइट SNR minus 2 and this will be d1 square d2 square, or you can write d1 square, or you can also write d1 d2 whole square, same thing.
प्लस जी सर उसी लिए मैंने सर 4 प्लस SNR नहीं आएगा दोनों तरफ एलसीएम लेकर?
नहीं एलसीएम मत लेना, आप अज्यूम करें कि SNR बहुत हाई है तो 1 निगलेक्ट हो जाएगा ना.
अच्छा ठीक है सर, ठीक ठीक
ठीक है. तो लिखा हुआ है हाई SNR. ठीक है,
ओके.
बॉन्ड लगा रहे हैं ना हाई SNR, क्या आपका बॉन्ड क्या है. जैसे हमने वो एक बॉन्ड लगाया था ना कि देखिए जी पहले तो हाई SNR पे गॉसियन आता है AWGN चैनल हो, बाकी रेली के लिए देखिए ना स्ट्रेट लाइंस आ रही थी. फिर हमने डाइवर्सिटी लगाई तो 1 ओवर SNR टू द पावर हो गया स्क्वायर 3 4 5 जितनी आप डाइवर्सिटी लगा लेंगे. अब आपने देखें 2 डाइवर्सिटी पाथ लगाए थे, आपको SNR स्क्वायर मिल गया यहाँ पे, और आप तो सिंबल्स भी 2 भेज रहे थे.
सर वैसे हमारा ऑब्जेक्टिव क्या है कि मोर डाइवर्सिफाइड की तरफ मूव कर रहे हैं?
नहीं, हम चाह रहे हैं कि प्रोबेबिलिटी ऑफ एरर भी मिले, हमें कम हो, यानी
ठीक है.
डाइवर्सिटी गेन भी नजर आए, और हमें एक और गेन भी मिले, इसको हम कहेंगे कोडिंग गेन, जो भी मैं आपको बताने लगा. और दूसरा है कि आपने अवेलेबल डिग्रीज ऑफ फ्रीडम को भी यूटिलाइज कर लिया ना
2L के
अभी.
लिए सर?
हाँ हाँ, यानी कि आपका L2 था और आपने 2 सिंबल्स भेजे, आपने जब एक कोड को डिटेक्ट किया एक्स ए को, तो एक्स ए को डिटेक्ट करने से दो मिल गया ना आपको, डबल ए मिल गया, ए मिल गया। अगर आप एक्स बी को डिटेक्ट सही करते हैं, फर्स्ट एक्स बी भेजा था आपने, तो यू विल गेट, you will finally know that yes, I actually sent minus a and plus a. So by detection a code over two time slots, you are getting 2 bits or 2 symbols. So you are utilizing your degrees of freedom as well as you are getting a diversity gain of 2. खैर अभी मैं आपको थोड़ा दिखाता हूँ इसको. So this is our error probability. So this factor is called the square product distance between xa and xb, where we know d1 and d2 are just the normalized difference between xa and xb, when the energy of the code is normalized to be 1 per symbol time. And this is also important. We will make sure that the energy of xa and xb is 1 per symbol time. And you will say how it is possible. So let us check how this is possible. Now this was my rotational matrix, this was my A, I multiply, this is my XA now. Now how I can find synergy of a vector energy? Square of this, and under root. If this is mod square, then no under root, no problem. So I am finding, mod square, so this will be just square. And I did all that. This is cancels, 2ab cancels.
सर आज के लिए इतना प्लीज.
Cos square plus sine square, so you will get 2a square here. हाँ जी, क्या कह रहे हैं आप?
सर नमाज
ओ
भी
अच्छा, 2
पढ़नी.
बज गए. हाँ, तो मैंने तो पहले पढ़ ली, मगर मुझे ये नहीं आ रहा कि 2 बजे तक क्लास है आपके पास है. ऑलराइट, थैंक यू. आई विल एंड दिस लेक्चर.
ओके, थैंक यू सर.